Hi, welcome to this chemistry lecture series. In this video, we're going to go over chapter 9, section 3, which is going to look at how temperature affects the rate of a reaction and how collision theory can explain this phenomenon. Now, let's get started. In order to talk about temperature and its effects on rate, we need to be able to talk about the kinetic energy of the molecules in a sample. So essentially what we're going to be looking at here is the kinetic energy or the energy of motion of molecules in the reactants of a reaction. The average energy of a substance is always constant and is dictated by the temperature. So whenever we read temperature and it's 20 degrees Celsius or 30 degrees Celsius, that is a measurement of the average kinetic energy of the molecules in a sample. If we're measuring the temperature of reactants that are about to react, we are looking at the kinetic energy of the reactant molecules. At any given temperature, even though the temperature is the average kinetic energy, that average goes up with higher temperature and down with lower temperature. But in reality, the kinetic energy of the individual particles is not all the same. Not all particles in a substance are going to have the same kinetic energy at a particular temperature. So let's say kinetic energy is 200 joules on average for 20 degrees Celsius. Not every particle is going to have 200 joules of energy. Some are going to have 400, some are going to have 80 joules of energy. And so that's where something called a Boltzmann distribution comes in. A Boltzmann distribution is a statistical graph of the kinetic energy of the molecules. The definition of a Boltzmann distribution is a graph showing the number of molecules with a particular kinetic energy plotted against the kinetic energy. So essentially, this is what a Boltzmann distribution is. The y-axis is the number of particles, so whereas the higher up the graph goes on the y-axis, the more particles are in that particular section. And the x-axis is the kinetic energy of the particles, meaning that the farther to the right we go, the higher the kinetic energy. So the shape of this graph, what it's showing us is how the kinetic energy, how many molecules have a particular kinetic energy, and how many molecules have a low kinetic energy versus a high one. The particles that are below a specific energy can be represented by an area. So, for example, when we read a Boltzmann distribution, we're not going to read it like your typical graph. We're not looking at an x and y intercept. Boltzmann distributions are what we call integral graphs. We're looking at the area below the graph before and after a specific point. So what are we going to have with a Boltzmann distribution? We're going to have the y-axis, which is number of particles. We're going to have the x-axis, which is the kinetic energy. And then we are going to define specific areas. We do this by, on the x-axis, putting a line, vertical line, that's going to show us the activation energy for a reaction. The activation energy is the minimum energy that colliding particles need to have in order to react. So going back to the collision theory, the activation energy is the amount of energy that two particles have to have when they crash into each other in order for them to have a successful collision. That means if we look at the Boltzmann distribution here, any particle below to the left of that activation energy will lead to an unsuccessful collision. They do not have enough energy when they crash to actually react. Whereas any particles above that activation energy are going to lead to successful collisions because they have enough energy so that when they crash, they actually react with each other. So that vertical line that represents the EA, the activation energy, is kind of the deciding factor. And this is what I mean by we look at the area under the graph. So let's say that this graph, if we get the area, just so you get the area of a square or a triangle, let's say that is 100 area, right? So if we look at this EA, let's say 80% of the area of this graph is before this EA line, this activation energy line, and 20% of this area of the graph is after the activation energy line. What that means is that 80% of the collisions in this reaction are going to be unsuccessful, whereas 20% of the collisions are going to be successful. That's how we read this graph. We're looking at the area under the graph before and after the activation energy. Now, are they actually going to ask you to calculate these percentages? No. We're not going to be asked to calculate how many or what percentage of particles will have successful collisions. What the point of this graph is a sketch to give us a visual representation of how the distribution of kinetic energy in this sample looks like. And so what you often use Boltzmann distributions for is that we don't look at them individually. We look at a comparison of Boltzmann distribution, a before and after per se. So let's look at how we compare them. The most common comparison for Boltzmann distributions is to look at the same reaction at two different temperatures, one above the other. So a low temperature and a high temperature. As the temperature of a reaction increases, the Boltzmann distribution shape changes. So let's look at these two Boltzmann distributions here. The dashed blue Boltzmann distribution, which we saw, I believe, earlier here. This dashed blue Boltzmann distribution represents the kinetic energy of the particles at a specific temperature T. The Boltzmann distribution in purple represents the kinetic energy of the particles at 10 degrees Celsius higher, at a higher temperature. So T, the blue one's a lower temperature, purple is at a higher temperature. Notice that the shape changes, right? We still have the general hill shape to the Boltzmann distribution, but the kinetic energy, the distribution of kinetic energy in the sample shifts. And that makes sense. Why? A Boltzmann distribution shows us the kinetic energy, meaning the peak, it's actually slightly to the right of the peak, but I'm not going to go into the details as to why. The peak of the Boltzmann distribution can be seen as the average kinetic energy. So if we compare the peaks of the Boltzmann distribution, at a lower temperature, the average kinetic energy, which we see on the x-axis, is farther to the left, and I'm going to put this in blue so it makes sense, is farther to the left. Oops, no, that's kinetic energy, not temperature. So this is the kinetic energy at a lower temperature. On the other hand, the one for the higher temperature, the one in purple, if we follow that line, the average kinetic energy for the higher temperature is higher than the one for the lower temperature. And that makes sense, because at a higher temperature, the temperature being a measurement of kinetic energy, of average kinetic energy, a higher temperature Boltzmann distribution will have a higher average kinetic energy than a lower temperature Boltzmann distribution, because temperature is literally a measurement of average kinetic energy. So we can see how in the Boltzmann distribution that has a higher temperature, that shifts to the right. We get a higher kinetic energy average for the higher temperature than we do for the lower temperature. But that actually changes more than just the average kinetic energy. The speed of the particles is based on their kinetic energy. That's what kinetic energy is. It's the energy of motion. So when we have a higher temperature, the average kinetic energy rises, which means that the average speed of the molecules also rises, which is going to increase the frequency of collisions. So that's the first reason why temperature and rate have a direct relationship. As temperature goes up, so does the rate of the reaction. Why? Because the average kinetic energy is higher, meaning that the particles are moving faster, leading to more frequent collisions. But that's not the only thing that happens. If we look at the higher temperature Boltzmann distribution, you'll notice that if we look at the activation energy, there is a bigger area past that point than there is with the lower temperature. So if we look at the area past this line for the blue, which is this, that is a much smaller area, a much smaller percentage, so smaller percentage, than the average, than the higher temperature, which is in purple. This is a bigger percentage. That means that a larger percentage of particles, of collisions for the higher temperature are going to be successful than for the colder temperature, because more particles have higher than the activation energy. There's an increase in the rate of the reaction because there's a greater portion of successful collisions, since more of those particles have enough energy when they crash into each other, which is one of the two things, according to collision theory, that are needed. An increase in temperature results in an increase in mean energy of the particles, or average energy of the particles, meaning a wider spread with a bigger percentage of particles having enough energy that is going to be above that activation energy. So we talked about that 80-20 split in the other one. If you raise the temperature, then the split becomes more like 70-30. And with bigger percentage of the particles having enough energy to surpass the activation energy, we get a higher rate of reaction. So the Boltzmann distribution helps us visualize the energy of the kinetic energy of the particles that are reacting, and why the rate of a reaction is going to increase along with temperature, because more of the collisions are going to lead to successful collisions, because a higher percentage of the particles have higher than the activation energy. So as temperature, and let me use a different color here. So with temperature, as the temperature increases, so does the rate of the reaction. So as temperature goes up, so does the rate of the reaction, because the particles are moving faster, which leads to more collisions, and therefore more successful collisions. And because more of those collisions, more of those particles are above the activation energy when they crash, leading to more successful collisions, and therefore making the rate go up. So this is how we explain the relationship between temperature and rate according to the Boltzmann distributions and collision theory. Now, you will be asked to draw these. One of the more common things that you have to draw when it comes to Boltzmann distributions is that they'll give you one of these distributions and ask you to draw the other. So they might give you one distribution and then ask you to draw one at a higher temperature. They might give you a distribution and ask you to draw one at a lower temperature. So let's look at how we sketch these. How do we draw these Boltzmann distributions for the AICE exam? First of all, understand that Boltzmann distributions are sketches, meaning that they don't have to be perfect, but there are certain things they're looking for. So here we're going to look at two Boltzmann distributions, the blue one at a lower temperature and the red one at the higher temperature. And we're going to look at what points should you look for when you're drawing these Boltzmann distributions. Now, the shape is always going to be the same. It's going to be a hill, and then it's going to slow down, but it's never going to touch that x-axis. So it's going to be a hill that then slows down and slowly flattens out. Now, all Boltzmann distributions have to start at the origin, because there are zero molecules with zero kinetic energy. At any temperature other than absolute zero, all particles have motion, and therefore all particles have kinetic energy. So Boltzmann distributions have to start at the origin. Whether it's a high temperature or low temperature, it has to start at the origin. That's the first thing we're looking for when we draw a Boltzmann distribution. So if they give you the blue one, and you have to draw the red one at a higher temperature, make sure that you're starting here at the origin. Number 2, we are only ever, because you're usually going to be drawing two of these, the two different temperatures, on the same axes. So when we draw these, they should only ever cross once. The two distributions, other than obviously at their origin where they start, should only ever cross each other once. So you can see here how if we had the blue one and we went to draw the red one, once we pass this point, the two distributions should never touch again. And you can see how that is the case. That red one, after that point where they cross, they never touch each other. That's another thing they're looking for on the AICE exam when you draw the Boltzmann distributions for two different temperatures on the same axis. Now, those are the two things that are going to be the same. Let's talk about how are they different. How do they differentiate between the low temperature and the high temperature? The first part is the peak. So we already discussed how the peak is the average kinetic energy for the distribution. So obviously a higher temperature needs to have that peak be farther to the right than the one for the lower temperature because it has a higher kinetic energy. But one of the things you have to understand is that these distributions have a set amount of area below them. The blue distribution and the red distribution, the lower temperature and higher temperature distributions, have the exact same amount of area below them, which means that in order to keep the area the same, if the peak is moved to the right for the higher temperature, it also flattens out, meaning that it needs to be lower, because that's how we keep the area under the distribution the same as for the lower temperature, which has a much bigger area vertically, but the higher temperature which have a bigger area horizontally, meaning that their areas are the same. So the peak for the higher temperature should be lower and farther to the right. So we can see that here. It's higher temperature, the red one's lower and farther to the right, whereas the peak for the lower temperature, the blue one, should be higher and farther to the left. And we can see that here, how the blue one is to the left of the red one and higher up. So that's another thing that they're looking for. Finally, the last piece here, when you're doing these distributions for different temperatures, is their tails, how they flatten out. When you're drawing two distributions, a higher temperature and a lower temperature on the same axis, the one with the higher temperature should end higher up than the one for the lower temperature, which should be lower down. So you can see here these tails. I'm going to remove the circles for a minute. The one for the higher distribution, the higher temperature distribution, is going to end higher up than the one for the lower temperature distribution, which ends lower down. And that goes back to how the areas work. Remember, the higher temperature is going to have a bigger area past that activation energy than the one with a lower temperature. And so the one with a higher temperature has to end higher to show that. This also goes back to them only ever crossing once. Because if you flip this and the higher distribution ends lower, they'll cross again towards the end. And you don't want that. So the higher distribution has to end with, or the higher temperature distribution has to have its tail higher up. The lower temperature distribution has to have the tail farther down when you draw them. So that's pretty much it. Boltzmann distributions can be complex because they are, they're integral graphs and they can be very complex to understand. However, once you get the hang of it and you understand that you don't need to master them, they don't need to be perfect, they're just looking for certain things, they become much easier to work with. Well, that's it for this video. I will see you all in the last video for section 4 of Unit 9 next time.